Hello and welcome to this edition of Using R. Today in this tutorial we're going to learn about distributions. Distributions are very, very important. For those of you who are in the, whether you're a statistician or not, whether you're a student of statistician, if you're doing data analysis, it is very important that you understand the concepts of distribution, but more importantly, you use distributions in order to generate your data, and you simulate data, you can practice with the data, you can do a lot of work using distributions. So, um, you know, learning and knowing about distributions is a very, very important piece of work that you must use. And R in particular is very well suited for not only teaching distributions, but you can actually use distributions in much more meaningful ways. So this is something that we are going to learn today in our R practice. So we are going to learn about distributions and how we can use distributions in R. So in the next, just want to give you a very, very quick introduction to who I am and what am I doing here, etc. You already know that, but it's a good idea to do this. And then what we'll do is we'll start talking about some theories about distributions and work with this. Note that in this lecture we are going to be dealing with a little bit of theory to understand what distributions are, etc. So do not be put off if theory is not your forte. Well, we'll see. So we'll do this. So my name is Arindam Basu. I am at the University of Canterbury at Christchurch in New Zealand, and this is a series of R, using R kind of tutorials for the MHRD e-Pathshala thing. So we'll talk some preliminary bits about what is meant by distributions and what we can do about these things. Then we will be demonstrating a few things here. So we'll demonstrate, for example, the different types of distributions that you get to see in R, because R has got an impressive array of distributions that you can work with and you can play with. When I use the word like play with, what I mean is this, that you can write code and you can execute that code and you can learn from the output of that code. In the process, you learn concepts, so you will be picking up bits and pieces of everything that you can do with this. And finally, we're going to summarize things that we find to be really useful to and really take away lessons and messages that you can use for your own work. So without much ado, let us move on to the objectives of this lesson. Here, in this lesson, we are going to learn some of the very basics of distributions in general. And then we are going to learn a little bit about the use of prefixes. So here you got like 4 prefixes arranged in alphabetical order from left to right. These prefixes are D, P, Q, and R. What do these mean? And the reason why it is a good idea to know about these prefixes is because these prefixes, when you use them with the postfixes, and postfixes are the names of distribution functions which are then abbreviated, can be very powerful. So because R has got many, many different distribution functions that they have already built in. For example, they use NORM, a norm, for normal distribution, POIS or POIS for Poisson distribution, BINOM, binom, for binomial distribution, and so on and so forth, you know that R is quite useful in teaching you about the different kinds of distributions. So we will be reviewing these things in a while, in a bit. We are also going to learn about demonstrations of a few distributions. Now, as I said, because R has got a number of different distributions in its fold, it is not always a good idea to give you everything. So in other words, it is literally impossible to cover everything that R has in its within it. So what we may want to do is this, that we are only going to give about 2 or 3 distributions, and we'll have to stop there. We can't do everything, anything and everything within that. There has to be a limit to what we can do there. Okay. What I want you to do, though, is this, that once you get a handle or hang of the different kinds of distributions we're going to work with, you will be using these in your own work. Okay, so you can go to our help files, you can use Google, you can go to the mailing lists, and you can find about them. That's not too bad. So let us talk a little bit more about these prefixes. There are 4 prefixes: D, Q, P, and R. Right? D stands for the probability density function. Q stands for quantile function. P stands for cumulative density function, and R stands for generating random variables. Now, in general, so if you are not really, if you're wondering as to, well, what is about a distribution, so let's talk a little bit about the distribution bit. Well, a distribution is more or less kind of a frequency distribution. So if I were to be a little bit more pedantic, I'd say that a distribution is like a frequency distribution. And this refers to how often certain observations, or how likely certain observations are going to occur in certain ranges of values. Why is this important? Say, for example, we are going to study in order to find out, how many, or what is on an average the body mass index of people. And we know that body mass indices, which are like kind of an indicator for how obese a person is, or how overweight a person is, it is a good indicator. So what people do is they take they weigh people, they note their weight in kilograms, and then they divide it by the height, which is then squared, to give a sense of that, okay, for a given particular height, what is the average weight of that person. If that weight is very high, then that person is obese or overweight. If it is very, very low, then that person is thin. There are, of course, other measures, but this is one of the ways in which you can measure the fatness of a person. So let's say you want to measure that, and maybe your client or you or whoever, we can't guess at this moment, they would like to measure this in a group of people. So what you do is you take about 100 people, and after taking those 100 people, you give them that measurement, and you note that value for 100 people. Now, beyond this, you will see that there is a range to which it can happen. So that the BMI will have a range. It cannot be, of course, less than a certain value. Like a value of 0 is impossible. And then you have because that means that there is no BMI. There's no existence, which has got a very specific characteristic as a variable. It's called a rational variable. And then you have you can go beyond certain values. But again, I mean, it's very unusual to have somebody with a BMI of something like, say, I don't know, like 50 or 70. It's impossible, right? So there has to be some range across which these values are going to occur. But what is important is this, that if this sample from which we are drawing the inference is going to be representative of the entire population, then we should know the probability of occurrence of an individual with the same characteristics. Like if you find somebody who's got a BMI of say 35, okay, then you will see you like to really figure out, well, if this sample is representative of my entire population, what is the probability that I'm going to see somebody who's got a BMI of 35 or over? So that has to be kind of the probability distribution of, or that probability has to reflect the probability of finding somebody in my sample of a probability of 35 or over. This is what we mean by the probability density function. So it has to be, therefore, this probability distribution has to be in the form of a curve that we can draw. The curve will have an area of 1, and the function that will draw that is the probability density function. R has a function for drawing that, and that is called d, say, binom or norm or I don't know, poise, depending on what you want to do though, or what kind of distribution you're working on. There is another thing which is equally important, and that is the quantile function. So which means that I've got a value and I know that that value has arisen from a certain probability distribution. I would like to see that where in that probability distribution curve am I going to find that value? And that is quantile function. So I will use the Q, and if I know that that particular distribution from where that has arisen, I will use Q, and that density function, that density or that distribution, like norm or binom or poise or whatever it is, to do it. Then there's a cumulative distribution function, which is very, very commonly used in teaching of stats. So we'll say if it is a normal distribution function, so what is the probability of the cumulative distribution function that we need to find out. And then and a fourth one, which is particularly useful for many of us who work in statistics, and if you're interested in to generate data, is to use is to generate random variables. That is very important, and so generation of random variables is very, very important because you can rapidly create data sets, you can simulate, you can do a lot of things with the random variables. Okay, so that's very important, and I'll show in a bit that you can actually use this in order to generate data sets that you can then use in a number of different contexts. You can iteratively build data sets using the distribution functions. You can simulate data sets using distribution functions. You can test your assumptions using distribution functions. You can do a number of different things that are very, very useful in order to generate distribution functions and using a notion of distributions. In the next slide, I'm going to show you that we are going to use R in order to generate a random distribution of samples using the binomial distribution function. Here, we have chosen that we are going to work on what is known as a binomial distribution. Binomial distributions, for those of you who are not familiar with binomial distributions, is a distribution where where we talk in terms of an event which has got a fixed probability. Think of a team playing a match or a game with maybe a cricket match, for example. You would like to find out what is the probability of that team winning against another. I mean, Of course, I mean, for each match, the probability is going to vary, but let's say you want to have and assign a probability. And what you want to do is this, that then you would like to create a universe of, what are the possible values of that win. Yeah. Another simple example, which we have used in this example, is an activity such as a coin toss. If you take a fair coin and toss it, then the probability of head is 0.5. What if you ran that experiment? So taking up picking up a coin, throwing it up in the air, a fair coin, and then throwing it up in the air and then testing it is known as an experiment, is referred to as an experiment. Let's say you ran 10 such experiments. In every run of that experiment, you expect that there will be a 0.5 probability that a head is going to be, you'll get a head. You ran that experiment 10 times. Okay, you expect to see head all of the 10 times, or all of the time, or you may want to see seeing a head none of the times, or you may see head falling like 5 times, or 4 times, 3 times, twice, once. So those experiments are very, very important, and you record them. Like out of those 10 runs, I have got like head 5 times. I've got head like 6 times. You record that. And then what you do is this, that those 10 runs of experiments are repeated 100 times. And you, for each of those 100 times, you record out of the 10 times how often you got a head. This sounds very tedious. And it may be a good experiment to run the binomial process, but it is not something that is quite an easy thing to do in real life. But this is a model. So this is a model of a binomial series of events happening, or binomial probability. So you may want to spend some time doing that. And you can do that in R very easily. So we here are going to generate like a binomial sequence of heads and tails, and we do that. So we say R, which is a random. R stands for randomness, or generating random samples. This is the prefix. Then we use what is known as binom, which is like the binomial distribution. We say that. We use that as a function. So we say R binom, which is a function. And then we say that we are going to run these series of 10 experiments 100 times over. So our entire sample space is 100. We could make it 1000, we could make it 500, whatever that is. But we are only going to use 100 times of those. How many runs of that experiments we are going to run each time? We specify that to be 10, which is going to be our size. So we'll run this particular experiment 10 times over. And then we assign it a fixed probability, which is of 0.5. So it is a very simple coin toss experiment that we are going to generate and simulate. So if we were going to event or simulate an event that has got 0.5, which were repeated over 10 times, and the whole thing got repeated 100 times over, then this is what we would do. And we store the outcomes of those experiments in the object called AA. And then we see the A. We examine A. So we took a model, and then we generate about 100 data points. But it's time now to see whether my data fits the model. We know that in a binomial experiment, the mean of the values is going to mimic, or is going to be equal to n, which is the number of times or number of runs of that experiment. In this particular case, 10 times the probability of occurrence of the desired event each time. So it's n times p. And you can see that the mean is 5.13, which when rounded down is going to be 5. It's not going to be exact 5, but it's going to be a ballpark, because what we have done is we have generated a series of raw data that then we are going to fit into the model that we think were used to generate the data. We also have a means of testing the variance for that, and we can use very simple functions such as var in order to do that. So var, and then we use the whatever that object was, and you can see that we are going to generate 2.31, which is, in an ideal world, it would be like 2.25, because 0.5 is the probability that that event was going to happen. 1 minus p, that is again 0.5, would be the probability that that was not going to happen. So together that was 0.25, and then we would multiply that by 10, so we get 2.5 as a variance. Here we get 2.31, which is not very far from 2.5. It is not going to be accurate because it is the data that we're going to feed to the model that we think generate the data. Kind of circular logic, you could kind of argue that it's kind of going back to the same thing over and over again. However, this demonstrates the idea that you can actually take a model, generate some data, then test the robustness of that data to fit the model, and then can work with this. We'll use another example to show how this works in the next slide. Here, we have used a Poisson process. A Poisson process is something like an event occurring, someplace. For example, people falling sick, or people leaving a hospital, or deaths as a result of surgeries, or deaths as a result of stabbings, something like that. Those are Poisson processes, events that occur. So here we have simulated using the Poisson distribution as a model. We draw 100 values with a lambda or an average of 5. And we have again used a random space where we have generated about 100 data points with a lambda of 5. And you can see that it's a very, very simple thing. We use a prefix of r, and then we use the a POIS process of POIS, and then so we set n to be equal to 100, lambda equal to 5, and then pp equals, and then we get as many number of events as we get to see. Again, if you take the mean of this, you see that the mean comes out to be like 4.88, which if you round up is going to be 5, which gives you the mean, and you can test the NP, which is the random process. And in this particular case, the mean and variance are almost equal. Again, 4.18. Ideally, that's how our Poisson process works. So once more, you get to see that that this distribution was a Poisson distribution from where those data were taken. What we are going to do here is we are going to now show you that you can do pretty much the same thing when you use a random normal distribution of values. So that's the next thing that we're going to do. But we're also going to show you some other things. So here, what we have done is we are going to generate a random sequence of numbers which follow a normal distribution. We are going to again generate about 100 data points that will follow a normal distribution pattern of a mean of 10 and a standard deviation of 5. The best way to do this is use the R-norm function. So norm, of course, is the normal distribution. R stands for the generation of a random sequence of those numbers. You want to generate a sequence of 10 numbers which will have a mean of 10 and a standard deviation of 5. So you specify them. This is how you write that, BB. And you store the results of those in an object called BB, because everything in R is an object and all objects have got their own classes and properties. So once you have generated BB, then you know that this is your sequence of the numbers. So if you take variance, you see it's going to be like 23, because that's very, very close. Because this time you've actually generated a sequence of data which then have got their own variance and norms. But see that we have also done something else. Here we have used a quantile function of the normal distribution, and we have stored that into an object called QBB95, which means that if we want to see that there is a 95.95 is the area that we have covered what is the quantile point at which that, for a normal distribution, that point is going to occur. And you can see that when we do this, it tells us that it's 1.64 or 1.65 to be honest. And that's exactly where it's supposed to be. So it's no wonder. This is how you find out the quantiles of normal distributions. Use Q and then the distribution that you want to work out. So I leave it to you as an example for some other things like Q binom or Q poise, etc., etc. Next, I'm going to show you another issue which is very interesting, which is like multivariate normal distribution in R. It is very important and very interesting. And we'll use some of these things. The multivariate normal distribution of R essentially is about is where you get two variables. You create a matrix, and then that matrix will give you two variables that are equally normally distributed. So bivariate normal distribution is what we are going to here work with. And in order to generate that, you give R a vector of means, and then you give them a covariance matrix. So we create the first covariance matrix, which is known as, which I've given an object name of my sigma, and we have formed and coerced a matrix of one and two variables are kind of related to each other by 0.8 as their covariance, and then we have given it created 2 by 2 matrix, and then we have given them a vector of means. We can obviously understand that this can be extended to as large as we can. So you can actually create a much more complex set of matrices. You can actually take a matrix from, say, a paper and then put it in here. And then what you do is this, that you use the MVR norm, so multivariate R normal data to put in as many data sets as you, as many data points as you want. Here we opted for 100. You could have opted for like 1,000. So it would actually mean that you could actually create a much more complex covariance matrix that you could generate from any table, any paper, and then you could get to that paper and find out what were the means of the various variables that the people had put up, and then you could simulate that data set. Yeah, a random sequence of that data set. You could actually virtually simulate that data set from the descriptive statistics, and you could actually run the same analysis in your R yourself. It's a very powerful way of actually testing your testing theories. So so I hope it has given you a sense as to that there are a few things that you can do. I mean, you can use a binomial process for that matter for studying, say, prevalence estimates of various occurrences and creating models out of them and creating simulations. So here are the takeaway lessons that using distributions is a very, very powerful thing that you must do if you're practicing statistics. Particularly if you use things like MVR norms, they're very useful in creating data sets. You can set up models, and then based on the models you can generate data, and then you can test this data to test the validity of other models, etc., etc. You can learn about exact probabilities and different distributional assumptions using R. So in summary, we have learned about distributions in R. We have learned that you can set up models and generate data using distributions. You can find out about probability estimates and quantiles and boundary conditions in R from your distributions. You can create data sets using multivariate normal data. So what I'd like you to do is to now start practicing using your distribution functions. Thank you very much for paying attention to this.